Hello, good evening or good morning everyone. I don't know the time for you guys, but well, this is my second video. This is demythifying maths. I'll be covering Coulomb's law and Gauss law today, or Gauss law, depending on whatever you want to call it. By the way, this is going to be much shorter than the previous video, which was on the Lagrangian, which was almost an hour long. Right, okay, let's begin. So, first of all, Coulomb's law. Coulomb's law is an observational law. It's the most fundamental basic law of electromagnetism or electrodynamics, I would say. So the first ever observation that was made was actually this, that the force experienced by two charges, let's say these are our charges, Q1 and Q2, the magnitude of that force is inversely proportional to the distance between the two forces squared. This was the first ever observation made. Then, with further observations being done, they realized that this is also proportional to the charge, or the charge of the body itself experiencing the force, or the charges around the body that would be affecting it. So this was the second observation. Now these two observations are what led to what we today call Coulomb's law. And now I've written it properly here. So I'll just explain it really quickly too. So F being force, of course. The force experienced by let's say a point charge Q2, which we've drawn here, due to another point charge in its vicinity, Q1 at position R1, would be this constant. This will be called Coulomb's constant, by the way, which is 1 by 4 pi epsilon naught. Epsilon naught refers to the permittivity of free space. It is a constant that I'll just be explaining in a second. And then we have the rest of our equation, which is Q1 times Q2, which we already stated here, that as observations were made, they realized that force was directly proportional to the charge of the body itself experiencing the force and the bodies around it, which justifies the reason we have the Q1 and Q2 quantities here. And this is the radius vector from charge 2 to charge 1. So it would be I drew it the opposite way, sorry. It would be this vector, R21, right? And squaring that basically just means taking its magnitude and squaring it. And that force obviously has to be in the direction. So this F21, I'm just going to erase the radius if that's fine. This F21 force obviously will be in the same direction as the radius. Oops, sorry. Yeah, as the radius vector towards Q1. Now similarly, since Q2 is experiencing a force due to Q1, Q1 should also experience a force that is equal and opposite to, well, F21, or the force experienced by Q2. That is because of, well, the most obvious law, that is Newton's third law of motion, that is each and every force should have an equal and opposite reaction. So we have the opposite force going as well, that Q1 will experience a force due to Q2 that will be of the same magnitude as F21, but it will be in the opposite direction, because as you can see, this was our R21 vector first, but since we're using R12, it has to go this way, which means the direction is reversed. So for that reason, we have negative F21 here. Okay, I hope that's clear. And so similarly, we have the same force F12. So these charges are attracted to each other. Well, I mean, I've just drawn it in this way. They could be attracting or repelling each other depending on the charge that each of them carry. Alright? Let's go further. Right. So now that we've defined this quantity, force, let's also just define the 1 over 4 pi epsilon naught. This is our permittivity of free space constant, and I'll just have to look up its exact value. I'm sorry, I don't remember it. One second, please. Yes. Okay. Coulomb's constant, it has an approximate value of, I think it is, yeah, right here. It is around 8.987551,787 into 10 to the power 9 Newton meter square per Coulomb squared. Okay. Now I'm assuming you guys are familiar with these units, but just in case you aren't, Newton refers to kg meter per second squared, which is the unit for force, right? And then we have meter square. I'm sure you guys are familiar with meters. It's just a unit of length, so this should be a unit of area because it's squared, correct? And per Coulomb squared, I hope that is pretty clear why that is, because then it that makes sense with the unit of the equation itself as well, and I'll just show that it does, because we have newtons meter square per Coulomb square, and we have Coulomb into Coulomb because of the Q1 and Q2, and we have R12 squared, which is meters, right? So we have meter square again, and we have the R hat now, so we get meter again. So the meter square and meter square should cancel out, finally leaving you with the coulombs also should cancel out, so it should give you Newton meter. Oh, sorry, I'm so sorry. Just Newton. My bad everyone. Yeah, there shouldn't be a meter here, because it's a unit vector, correct? So you don't have to worry about it. Or more importantly, you can actually write this as meter cubed times meter, which means you can cut this out, get this to 2, and then you can cancel this entire thing out and this out. Okay? Sorry. So sorry. Right. Now let me also just explain permittivity of free space really quickly. And you might also wonder why the 1 over 4 pi is there. That is for a very specific reason. That is, when you use Gauss Law, you will see very soon that the 4 pi is quite important, because it lets you cancel out a quantity quite easily. And I'll just give you the permittivity of free space as well really quickly. Right. So this constant is about 8.85418782 into 10 to the power negative 12 per meter cubed per kg seconds to the power 4 ampere squared. Okay, I hope you guys are aware of this. I hope you guys are aware of these units, because now I'll just explain what this constant implies. It basically, permittivity. Think of what permittivity means. The ability or allowance, basically, of free space. So in this case, because we're talking about electric fields, obviously this is supposed to imply something related to the ability of electric fields. So permittivity of free space would basically be a constant that shows the ability of an electric field to pass through free space. Alright, there are mediums which affect the ability of electric fields to flow through them. And for that we use epsilon naught times epsilon r, where epsilon r refers to the relative permittivity of the medium involved. But that is much later in electrodynamics, so I'm leaving that for now, because that is not exactly something we're interested in for now. Okay, so continuing on, now let's think of not just one force, like one. Right now the example we considered was just two point charges affecting each other. What if we have, let's say, Q1, Q2, sorry, I'll just make it bigger, Q2, sorry about the sizes, by the way, they're just, imagine they're point charges, okay? Sorry. So let's say there's 4 different charges, correct? So now each of these charges should affect each other, right? It's not like you can only have Q1 and Q2 affecting each other, because all of these are in each other's vicinity. So what you'd have to do is basically, because force is a linear quantity, if you don't know that, force is a vector that is a linear quantity due to acceleration being a linear quantity. So you can have that the summation, the total resultant force on any body should be F1 plus F2 plus as many forces as you have affecting the body, which you guys should be familiar with through regular mechanics itself. So we have, so Q1 is affected by Q2 because, so let's just say this is F1 because it's being affected by Q2. Now Q4 is also in its vicinity, so it should also have F4 affecting it. But then Q3 is also in its vicinity, so it should also have F3 affecting it. So since we have so many forces being applied on one another, we kind of get that F1, now I'm using 1 to refer to the fact that this is the force experienced by charge 1, should equal to, I'll just be writing 1 over 4 pi epsilon naught as k, if that's fine for now, the Coulomb's constant. This one, I'm just writing it as k for now, just to make it easier to do the maths really quickly. So k, we have Q1, Q2, and we have R, which one was this? Right, 1, 2 squared, R12 hat, plus K, Q1, Q3, R13 whole square, R13 hat, plus K, Q1, Q4, R14, sorry, I wrote 2 by mistake, 14 whole squared, R14 hat. Sorry, I keep writing 2, I don't know why. Anyways, so you can obviously see that K can be taken common and Q1 can also be taken common in this expression because they're being repeated one by one. So we get that this is actually KQ1 summation. I'm going to use summation notation just so that it's easier for me. Over I, summation of I, where from QI of QI over R1I whole squared, the vector. So that would mean taking the vector's magnitude, basically, or dotting the vector with itself. Right. So now we wrote it in shorter form, and we can see that we can make basically a superposition of these. Now let's just put the K, because it's a constant, right? Let's just put it inside the summation. Shouldn't be a problem, right? We've done that before multiple times in our previous videos, or well, previous posts, not videos, sorry. So you get KQI by R, we got 1I, R hat, 1I. Now, we've basically turned force into Q times some quantity. Now this quantity we define as the electric field vector. We write it as E with a hat on it. Right? So we have essentially turned our very complex Coulomb's law into F equals QE. Very simple, very easy to understand. And I know this seems kind of abstract because we just have some random constant being multiplied by charge and then being divided by the radius vector squared and being multiplied by r hat. So it seems kind of weird that we have such an abstract concept. So just to give it some light, or like to give it some point of understanding, think of this electric field vector as being the force that one unit charge, by unit charge I mean a point charge of 1 Coulomb, or any units that you prefer. I'm using SI units because they're more favorable. So let's say there is a point charge of 1 Coulomb called P entering a field, or a network of charges. Okay, so now obviously you can't be calculating this quantity through Coulomb's law every single time. So what you'd rather want to do is take this for different charges. Suppose I increase the charge of P to 2 coulombs, or to suppose 3 coulombs. Now you can't calculate this entire thing this entire value over and over again for different charges. So it makes more sense to define a quantity for this entire network of charges, and we define that as E. Okay, that should represent the average, or not the average, but the resultant force that is experienced by each unit charge entering the vicinity of this network of charges. Alright? Okay. So now that we've defined this electric vector, sort of, let's just draw one very simple electric field. Let's say this is the XY plane. Actually, let's forget the XY plane. Let's just say this is a proton, right? This is a proton with plus E charge, E being elementary charge. We don't know what E is. It's 1.6 into 10 to the power negative 19 coulombs, right? Okay, so if you have even a little bit of intuition, you know that current should flow from the positive end to the negative end, and that is conventional current, by the way. So similarly, that flow of current is dependent upon the electric field. So we say that electric field lines basically represent so now I'm gonna draw little vectors around this to represent that. Let's say so the tail of each vector represents what the force experienced by each vector on that point should be. Okay, so we will generally observe that for a proton in the middle of nowhere, all electric field lines should flow outward. And intuitively that should make sense, because unit charge means 1 Coulomb, right? So, and this is a proton, so it's positively charged. So if I placed a unit charge over here that is also positively charged, intuitively it should repel, right? It should go away from this, because they're like charges repel each other. So this is kind of the concept behind the electric field vector, that it represents the force experienced by each unit charge around or within the vicinity of a given network of charges. Okay, now let's say you have a plate, correct? I'll draw a better plate really quickly. Alright, now let's say you have a plate that is basically, you have some battery connected here that is making it so that these two plates have have charges flowing through them. So you should have this kind of an electric field forming, which is uniform, kind of going in straight lines, you know. So obviously current is also going to be flowing in this direction, which implies that electrons should be flowing from this end to the positive end. This is because, and this is in support with Coulomb's law, because Q is negative, correct? Q is less than 0, so F should be QE, and since Q is less than 0, F should also be less than 0. This is assuming that E is going in this direction, which is positive to negative. Okay, I'll just put an absolute value around it, or actually I'm not going to do that because that doesn't make sense to call a vector negative, but you get my point. The direction is reversed for electrons flowing in a circuit. Now you see these electric field lines being formed, so sometimes you'd want to know that, suppose through this plate itself, the positive plate itself, suppose you wish to know how much, like what magnitude or what is the sum of all these vectors flowing, of all the flux or all the electric field lines flowing through this. So for that, what you do is basically you would imagine this plate and you would assign a normal vector, which is n hat, to this plate and calling it n hat. That should be normal, so it is perpendicular to the surface of this plate, and you would dot it with the electric field lines flowing from it. Okay, and we call this quantity flux, or more specifically electric flux, and we represent it with a phi with a subscript e. Alright, so it kind of gives a value to the amount of electric field lines flowing into or flowing out of a given, I would say, a given surface, or just any given volume as well. Well, in the case of a volume, it would be a closed surface, because you still only want to take the electric field lines flowing through a two-dimensional body. Alright, so now we're going to introduce Gauss Law. Now what Gauss Law exactly says is that for any closed surface basically implies that there is a surface, suppose there is a surface S. Okay, now this isn't exactly closing some volume, is it? It's a flat surface, and it's just this. So this will be called an open surface, at least for this context. Now let's say you have a sphere, but it's hollow. Or let's just say you have a sphere, but you only want to consider this surface of the sphere. Now this surface of the sphere, you could call it S, But this surface does enclose a volume, which is this. Let's call that V. Okay, so suppose you want to you have you have some point charges within this surface. Okay, sorry, within this volume you have some point charges. I'll just call that Q. Okay, or let's have Q more. Let's just have more Q's. Okay, you have some point charges within this given surface. So now you want to find the flux from it, correct? So obviously the flux, as we defined, was the amount of electric field lines flowing in parallel to the orthogonal component of this surface. So what we would do is we would take an integral, and because I've defined this as S, we will not consider this disk, by the way. We're considering the sphere for now. But I'll be proving this for generalized for any general body, not just for spheres, just to be clear. So let's say for any general body S, you want to take the flux on it, and this is a closed body, by the way. So we take E dot n hat d sigma. The sigma is just a notation thingy. You can use S, you can use A, you can use whatever you want. And we know this is a closed surface, so we'll just add this circle here. Alright? We'll define this as our electric flux. Now, we know that the surface is closed, which means we can kind of exploit one of the properties of this kind of an integral. If you may remember from the divergence theorem, that for the triple integral over a given volume of the divergence of some vector, I'm just gonna call it A for now because I'm using E here right now, or an F as well. The divergence of some vector A over the volume V should equal to the surface integral over the surface of that given volume of A dot the normal vector or the orthogonal vector of that surface d sigma. Okay, so that is just divergence theorem, by the way. It's a theorem of multivariable calculus, which can be proved easily with the generalized Stokes theorem, which I have covered before on my Instagram. Please check it out if you can. So now you just want to evaluate this quantity. So obviously we're going to use the divergence theorem, because in general usually surface integrals aren't easier to calculate for closed surfaces compared to volume integrals. So let's just use that. We get a triple integral over the volume V. This is our volume V, by the way. The volume enclosed by the surface S is our volume V, and we have E hat, the divergence of E, the electric field vector, dV. Okay, now let's just consider the divergence of this electric field vector first. Okay, so if you know how to calculate the divergence, you should know that first we'll use the definition of the E vector. We have K, Q1, or basically sum of Q, right? Because we summed Q. And then we have R hat, and then we have, let's add Qi and Ri. Okay, this should make a lot more sense. So now we know K and Qi are independent of R, and any vectors that might depend on R. which is our radius. So we'll just take them outside of this, and it will become kq divergence of r hat by the r vector squared. Now I'm going to further exploit this a bit and say that it is the divergence of, r hat is basically just equal to the r vector divided by its magnitude, correct? And the r vector squared should be the square of its magnitude. So we just get, this is the divergence of the r vector divided by the magnitude of the r vector cubed. Okay? Now, there are a few ways to evaluate this, but the basic premise is that you will find, if you do this the regular way to calculate divergence, you will find this comes out to 0. But there's a special condition. That is only possible when r is not equal to 0. Because as you can see, we're dividing by the magnitude of r. So the magnitude of r, whenever it's equal to 0, this will kind of explode. This entire value kind of explodes. So that implies that there's a lot of concentrated things at our center. So the way to go about this is generally, I'll first prove this result for this specific identity itself, and then show you why this works. Okay, so forget the phi e vector the phi e quantity for now, and just imagine I am integrating over a sphere. Okay, a sphere of radius r. Okay, so we will take this in polar coordinates, or well, not polar coordinates exactly, spherical coordinates, and we know that is the integral of pi from 0 to pi and from 0 to 2 pi from 0 to r of the divergence of this quantity dr. Oh, I'll just add the r squared sine phi dr d theta d phi. Now this r squared sine phi is, by the way, just the Jacobian for spherical coordinates. It's just a standard thing. Alright, so now I'm going to use the divergence theorem immediately, because I just want the surface area of this thing. So I get pi, because at the surface area the radius is always equal to r, we don't have to really care about it, so we'll just go 2 pi 0, and we get r hat, absolute of r cubed times r squared sine phi dr d theta d phi. Okay, and just to be clear, we've already defined this r, capital R. This, actually I'll just change the symbol to rho, just to make it clear that the absolute of r is always, we've already defined that the absolute value of r has to be rho, so we'll make it to rho squared and rho cubed. Okay, so we have this cancelling out, and we get r over phi, and since r over rho, and rho is a constant because this is the surface, it won't change. We just get this. Oh, also just to be clear, this n hat vector, as you can see, this is parallel to the radius. So we'll just really quickly take this as n hat here, and then we can kind of just change this into r or rho, because, well, this is our sphere, this is the r vector, and this is the normal, and the normal is a unit vector. So you just have, and the absolute value or the magnitude of r, the r vector, is just rho. So we just have rho times r hat dot n hat, and r hat and n hat are parallel, so we just get rho. So we just have rho back here. Alright, and we get sine phi dr d theta, sorry, this dr shouldn't be here, d theta d phi. Alright, rho and rho cancel again. Now you just get left with pi 0. So there's no theta terms, so we can already get that aside. So we get 2 pi sine phi. Okay, and d phi. Now if you integrate this, you should get, obviously, that the integral of sine phi should be negative cos phi, negative cos pi should be negative 1. Sorry, cos pi should be negative 1, and cos 0 should be 1. So 1 minus minus 1, that gives you, negative 1 minus 1, that gives you negative 2, but it's multiplied by negative 2 again, by negative 1 again. So you basically get total of 4 pi. Right? Now, we just showed that this quantity, you found this to be 0 earlier, but we showed that if we integrate this, we get 4 pi, which means something is up, because something has to be up. You can't just get some quantity randomly like this. So how we prove that is that we'll say that this thing, the divergence of r hat over the of r hat over r squared, the vector r squared. Also, I'm so sorry, the notation is kind of confusing, but it's just like this in physics. I'm so sorry, but yeah. So we know that this is 0 everywhere where r is not equal to 0, which means this has to be kind of a graph like this. This is being 0. Okay, and it needs to explode here, because otherwise you won't get this 4 pi as the value of your integral. So we define some function delta r, or delta x basically, in such a way that the only time that it is 0 everywhere where x does not equal to 0, and it is basically approaching infinity when x equals 0. So that makes it possible for us to say that the integral all over space of delta x dx, sorry, again, notation is really bad. I'll just change it to t, that's better, dt is equal to 1. So because of this, if you multiply it by 4 pi, we should get 4 pi as our integral value, and that should fit our total, the equivalence of this. That should be equivalent to this function, because we have it exploding at one single point, which is r equals 0, or the r vector or the r vector is the 0 vector. So we can define this as 4 pi delta cube. Delta cube just implies it's 3-dimensional, of the r vector. right? Because the r vector has to be three-dimensional. Now this finally gives us that if we go back to our integral, we have to take the divergence of E. Now we took the constant aside here, right? So we have k, q, we have the integral of the divergence of r hat over r squared dv. And we already found this to be 4 pi. But that, just to be clear, that was only possible because the r vector went over the 0 vector position. And as you can see, this is a closed surface, right? So the volume of this surface should cover this point, which is the 0 vector point, where r is equal to the 0 vector. So we can carefully just say this is kq, and the integral of 4 pi delta cubed r dv over the entirety of the surface V, which is a closed surface, by the way. So r is equal to 0 is included. So this integral should just come out to 4 pi. So we have 4 pi kq. Now let's just remind ourselves of what q or what k is, the Coulomb's constant. It is 4 pi. So no, I'm just changing it. The Coulomb's constant was 4 pi times epsilon naught. And now you can see why the 4 pi is important, because you can just cancel this out and get this to be q by epsilon naught. And that is the integral form of the Gauss law for electric fields, that is. That is that phi of E, that is the electric flux for a closed surface S, should be the charges enclosed by that surface divided by epsilon naught, where epsilon naught is the permittivity of free space. Okay? Another thing that you can do further to get it into the differential form is to use this divergence theorem again. Write this as a triple integral over V of the divergence of E, the electric field vector, times dV. And you know that Q is basically equal to rho, where rho is the charge density, by the way. Charge density is basically, let's say, we have density for mass, right? Mass is defined as the integral of rho, where rho is the mass density or regular density, integrated over dV. So similarly, we're just saying Q is the integral over V of rho, where rho is the charge density, dV. So it should return Q. So we write it in this form, and we keep the epsilon naught because it's just a constant. And we see that this integral is also over V, and this R, the new integral, is also over V. So they're going over the same, we have the same bounds, and these two integrals are equivalent. So we can just say that the integrands must be equivalent too, because the bounds are the same and everything is the same. So we get that the divergence of the electric field vector should equal to the charge density of the given body closed body, by the way, divided by epsilon naught. This is the differential form of our Gauss law. Right. So that is actually it for this video. I'm so sorry, it's gotten quite long. 45 minutes, that's quite long for a video. But anyways, I hope you enjoyed watching this, and if you have any doubts, feel free to leave any comments, feel free to do whatever you wish to, looking up this topic, because it's honestly quite interesting and I would love to continue it more. I would probably be doing the Gauss law for magnetic fields next, and that is quite easy to understand actually. So hoping to see you all in the next video. Thank you for watching. Bye bye.